All right. So, so that is the average deviation. Now, the next step is to make the average deviation into the standard deviation. And so the difference is that rather than talking about the absolute value of deviation scores, we use another method to get rid of the negative deviation scores. We square them. And this procedure is illustrated in the table 5.9. Notice that the table is actually very similar to the other one. So the thing that we do differently is we are going to square the deviation scores rather than make them absolute values. Okay. So as you can see, we get a much bigger number. We get 5,580 instead of 2,200 and, or sorry, 332. So a lot different as far as the size goes, but you'll see that it's going to get pretty similar. All right, there's going to be a slightly different thing. And again, it looks really complex, but it's not as bad as it seems. So the standard deviation raw score, all you're doing is you're usually going to get given this information. All you got to do is plug it into the formula here and just complete the formula. Does everybody know their order of operations for algebra? So yes. So please excuse. So you're going to do parentheses first, then exponents, right? Then multiplication and division, and then addition and subtraction. So as long as you get those order of operations correct, the math should be correct for you. So you got to do what's in the parentheses first. So we got to sum x, right? And then we're going to square it. And then we need to do the exponents. So doing all that stuff in order, once we get the sum of x, 2,220, we're going to square that. And you can see every step right there. So it goes to the next step. After it's squared, we get 4,928,400 and 400. So that's the next step. And then we got to do the first set of multiplication or in division first. So we're going to take the 4 million, blah, 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 divided by 30. That equals 164 and 200, or 164,280. And then you have to look at it as 169,860 minus 164,280. That's actually like in parentheses. Then you have 5,580 over 30. You got to do the multiplication and division first. And then your little sign there for doing the square root is basically an exponent, even though it doesn't show an exponent. But it is an exponent. So you're doing the square root of 186, which takes you back down to 1364. And you'll notice you're always going to have positive numbers because that's in either way, you've always got to have positive numbers. Because otherwise, the different scores on the other side would cancel each other out, and you get zero all the time. So that is the standard deviation. And that's going to be important because a lot of statistics use standard deviation. Most of the time it's going to be given to you. It's just showing you how to get it, okay? Well, I can tell you this, your quizzes, unless I'm actually asking to do the standard deviation, you'll be given the standard deviation if you need it in an equation. So most of the time you're just going to plug stuff in. And probably most of the time I will also give you the equation to plug stuff into. So you won't even have to look it up, okay? What's that? Yeah, well, You know, y'all are not mathematicians and you're definitely not statisticians. We just want to familiarize you with the terminology. And if you really notice these 4 chapters, most of it's really just terminology. And so you can be willing to bet that most of the test is going to be, finish my sentence. There you go. There we go. I'm just seeing if y'all are awake. I can't see you guys, so I can't see if you're just really sleeping. All right. So now we have a look at curves, and you're probably going to get given a picture of a curve, and you have to name it. So mesocurtic, that's the normal curve. Average height, it's rather filled out all right. Leptokurtic, and I'm on page 124, is thin and tall. Plateokurtic is like a turtle shell. So if you notice in a normal distribution, the mean, the mode, and the median are all on the same spot. Now, when we get to the other page, page 125, we look at positively skewed distribution. The way to look at it is positively skewed, the tail end of the will always go to the positive side. Tail end, positive side. Tail end, positively skewed. And if you notice, the mode is on the left, the median is in the middle, and the mean is to the right. So another way to look at it too is wherever side the mean's at of those three, that is the positive side. On the negative side, the tail goes down to the left to the negative side. And again, the mean is on the tail side, so it's the negative. And the mode is on the right side and the median's in the middle again. So that is how all positively skewed distributions, all negative skewed distributions will look. Again, you're probably just going to match. I probably have 5 different pictures, and you're just going to match it 5 different ways. So, Caitlin, how was the test? Yeah, yeah. So, don't have to put it off to the very last minute. You can take your test. You'll be okay. You got all the time. There's none of them have a time limit, and they're all open books. So don't be afraid to take them. They vary, but they're all worth 25 points. And so you can imagine these tests, I'm going to make it as similar as I can to the other tests. So, um, yeah. Well, I did because I'm looking at all the tests and only 2 people have taken them. Yeah. So the Z-score. Now, the Z-score is a pretty important concept to understand because it takes raw scores and turns them into standard scores. And standard scores are based off of uh, the how the test is as a sample, but also can be as a whole population. So when we look at a standard test like an intelligence test, right? Intelligence is considered 100 is normal. That's the mu. That's the average. And then the standard deviation for an intelligence test tends to be 15. So 100 is the average, the mu, and the standard deviation is 15. So that means that at 85, if you got a score of an 85, that also means one standard deviation to the left is a -1 z-score. So I could take that and I could apply that to something else because now it's a standardized score instead of just 85. So the z-score means more than necessarily the raw score does. That's why we do the z-score. Does that make sense? Because you could have you could have another intelligence test that isn't based off of 185. It might be 50, right? And so the standard deviation is going to be different for that. But I could take that score on that test that says 50 and I can make it a standardized score, and then I can compare the z-scores between the two tests. Does that make sense? So, and because the standard deviation might vary a lot between the two separate tests, with the standard score, the score means the same thing because I'm talking about standard deviation units away from the norm. That's what the z does for us. So when you look at it, you've got your formula there for the z-score. So x minus x bar over s, and z equals x minus mu over sigma. And so the s and the sigma, the s is the sample. And so if you have a set sample, you know that what the s is for that. And the z on the next one down on page 127 is for the bigger population, for the overall population. So that's the difference. They're doing the same thing. It's just one is a sample and one is the overall population. Does that make sense? Okay. So so the S is the standard deviation for the sample, and it's used as a big S. The sigma on the second one is used to designate the standard deviation of the population, of the whole population. So that's the difference. So looking down at our example and the Z for English and the Z for psychology, they have all of the information. Again, you're going to be given this information. So you've got X, you've got X bar, and you've got your S. And the S, remember, is the standard deviation for the exams themselves rather than the whole population. So this English student got a 91, and we're trying to figure out what their score is, their Z score is. So the average was 85. So right there, I already know that my Z score should be a positive Z score because X is bigger than X bar. X is bigger than the average. So it's going to be a positive Z score. And then the standard deviation for that test for that group was 9.58. And this is where grading on a curve can come in. Sometimes we can use this to help us figure out how to set the curve so that people do better, right? And so we take that 91 and 85, and if you go back up to the Z English equals X over X minus X bar over S, 91 minus 85 divided by the Z score, or the S, which is 9.58. 91 minus 85 is 6 over 9.58, and that's going to equal 0.626 Z score. That's the Z score for this individual. Their psychology exam, it was an 86 for their score, and the X bar, which is the mu or the mean, is 74. So again, plugging in the numbers, 86 minus 74 equals 12. And the standard deviation for that sample, for that test, was 13.64. So 12 divided by 13.64 is 0.880. Again, you're just going to have to know how to plug the numbers in and get the right answer. And you can use your calculators. When you're doing this, use your calculators. You can use spreadsheets if you want to. I mean, there's programs you can do on Excel that you just plug in the numbers and it just gives it to you. So just make sure that you're using. No, go ahead. Yeah, that's just so you've got their individual score. X is their individual score, and you're minusing it. You're subtracting from X whatever the mean score was. So if the mean score was 91, it would be 0. And so they would be right at the mean for the whole test. They wouldn't have any standard deviation. If their score was below 85, if it was 80, it would be minus 5, and then minus 5 divided by 9.58, you're going to get a negative z-score, which just means that it goes to the left of the mean, of the center of the distribution. Okay? And remember, these are just for individual numbers, individual z-scores. Now, the z-score is going to come into play because later on in Chapter 8, we're going to talk about how to test a function, how to test a hypothesis using z-scores. So that's why we're doing it now here in Chapter 5. You can make it so that Excel won't just do it for you. You got to set it up to do it for you, but yes. Yes, you can, yes. And that you can just look up. I mean, you can just look it up online, and there's probably people out there that you can just copy a. I mean, be careful doing that, but you can probably just go to. Well, if you actually have Excel, you could go directly to um, Microsoft Office apps and get and download a sheet that does exactly that. I don't know if you can do that or not, but you can. So you can go and do standard deviation. You can go and of course you still have to plug all the numbers in, but it'll do all the work for you. But even then, most of this is relatively simple mathematics, especially when they give us like I'm not going to I will make it clear what they are. Okay? So chances are if I'm very clear with what everything is, you might end up having to look for the actual equation because I can't give it everything to you. But if I give you what you need and tell you what you're looking for, then you can just go, oh, that's a z-score, and then go to the z-score. And then a hint would be if it's not z-score, then the information that I give you won't plug into it, right? So then it'll be something else. So you'll get it. I'm not gonna. My goal is not to have you get tricked. I don't want. I always hate when my professors do that. I mean, what's the point? I'm not learning anything. So I want you to know how to do it, and or at least I want you to know when you read the data in a you go, oh, this is a t-test. I remember Dave said, it's a parametric test that these are the requirements for the z, and does it match? Was this really a z test or was it a t-test? So And the difference between using a z-test and a t-test is usually how many people or how many participants you have or how many scores that you have. So that's that. The reading probability. So on pages 130 and 131, we have all these different z-scores and the area. So when you look at a z-score, the area between mean and z, so at the very top of the table here on page 130, if a z-score is 0, there's no area between the z-score, but all the area beyond it is half of it, right? So as you keep going down that scale here, there's more area in between the median, the middle, the mean, and the z-score, and there's less area beyond the z-score, which makes sense because all of it together can only add up to 0.5 because we're looking at half of it, right? So if you notice, 0 and 5, 0, 0, 4, and 0.496, which equals 5. So don't get confused. Everything there has to equal 0.5 because we're talking about half of what's there. So the further away from z, the more area that's in there, the less area that's beyond that. And you need to know that because when you start looking up critical values, you need to know what's usually beyond that. Okay? So right now, this is just really good information and gives us some probability, but we're not going to use this until later on. Okay? Any questions on anything so far? You can just go to Microsoft Office if you have Excel and go to their Excel page, and they have all kinds of things that you can download as far as statistics go. So if you go to like, let me do it, Excel formulas, help. So if you just do like Excel formulas help, there's all kinds of stuff that just pops up. And so actually if I went Excel statistics, and put in templates, and then if you want to, you can actually go to find the actual Excel, Microsoft Excel. So templates.office.com. Funny enough, it's at the end of it. When I click on it, wait for it. So you can take a tour or you can download it. But there's lots of things that you can use it for. And when you actually get into like the Excel portion of it, you just ask different questions. And if you already got it, you can turn all that other stuff away. Sometimes you got to go through a lot of things before you get to where you need to go. But it's all there at the Microsoft Store, especially if you go to Excel Help, Microsoft Store. Trying to find something that, if I can find a good link to it, I'll post it. Right now, I haven't got past all the stuff that they're trying to sell me, but I'll look into it later. I just know how to plug it in and use Excel because I'm old. Long before I had all these fancy programs, we just had Excel. So, but now if we go to chapter 5, the test part, so page 138. Now, it's always good to remember there's this old way of looking at stuff, and basically garbage in and garbage out. So if you put garbage data into your program, what do you get? Yes, there we go. I was wondering, are you all still with me? Can you all see my Excel? All right, I got to figure this out then. Share. Do y'all see my screen now? Do y'all see Excel now? Okay. All right, so I'm just going to really quick put in all the data that we have in part 1 here. So 76. Say again. The test, page 138. All right, so 1, 2, 3, 4. 4 times 5 is 20. I got 20 numbers. So we're cooking with gas. All right. So now it's all jumbled up. First thing to do is get it all in order. So now we've got 62 to 80. Now we've got these numbers in order, right? So we can know that out of 20 numbers, the range is 80 minus 62 or 18. So we already know from the beginning what our range is. our range equals 18. If I want to know what the sum is, right, I just go to data and let's see, there should be something simple to do. Oh, there we go. AutoSum. So AutoSum automatically, usually it will automatically select everything for you. So the total sum is 1371, right? And so now if I want to know what the mean is, over here, I just put an equal sign in there, put my sum, and I know that I have 20 numbers, right? So the mean is 68.55. Pretty simple. So if we have 20 numbers, right, then what is our mode? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's an even number, so we've got 10 and 11, and they're both 67. So that's good for us. So our median, sorry, I said mode, I meant median. Our median is then 67. See how easy it is to get data when you have it on a screen? And so then we have mode, right? Which one is the mode? Which one occurs the most? Well, we've got 364s, 465s, we've got 367s, I think it's 65. So just out of that, we have our data, right? All of our descriptive statistics. We have the range, the mean, the median, and the mode. And what do y'all think about that? Okay. So now we know what our mean is, right? 68.55. And if we want to know what our average deviation is, right? Not our standard, but our average deviation. What is that? It is this is our score minus the mean, right? X bar. I'm just going to put mean because I don't have the time to set it up and make it look pretty. So now we know that our score is going to be equal to this score because that's our score, right? And it's going to be minus what? The mean, which is 68.55. And that's our start of our scores here, right? Now I can just drag it all the way down to that. So these are all the things that are distanced from the mean. Now, if I show you what happens because they're negative right now, right? So if I show you, formulas. If I auto sum it here, it's going to be pretty close to 0. It might be off a little bit. Yeah, so it's off just a little bit. If there's there's 14 zeros, so 14 zeros, 5, 6, 7, 8. It's pretty darn close to 0. And that's because these negatives cancel the positives out. Do you see that? So that's why we can't just add this up. We actually need to take the so looking at this, we can see all of these. There's different things here, all for the statistics. Y'all see all the different things for statistics? There's a z-test. Hey, we're going to need that. There's a t-test. So all of the stuff's right here for us to use. We just need to figure out how to use it, right? So now what I need to do with my data, though, is this won't work. I need it to be, I don't know if I can do it this way. So we'll try. All right. So there must be an absolute value here someplace. It's been a long time since I've used Excel. Oops. Come on to bed. Absolute value. So that's even better to use that. So now we're going to do the absolute values instead of so now it's positive, right? So now we'll do that again. Now they're all positive, and now I can actually get a sum. So actually, I should put absolute value. Does this help anybody? Okay. So now I can sum it up, and now we have our sum of the differences, right, is 80.3. So let's go back to our average. A little bit further. So now our average deviation, we're going to take the sum of this, so 80.3, and we're going to divide it by n. So our average deviation is going to be equal to this number divided by 20, right? So, yep, divided by n. So now we've got our average deviation. See how simple that is? Okay, so now we're going to do standard deviation. So sigma. So that is going to mean that we need our numbers back. So we need x minus x bar. Not at the absolute value this time, we just need the regular value. So we need, put our equal sign in, select the first number, and it's minus the mean again, right? So 6.55. It's going to be the same thing, only now we've got our numbers back. Something happened here that wasn't supposed to happen. Let me see. A2 minus, oh, I know what happened. We won't do it that way. We'll just plug it in, 68.55. So there we go. That looks better. Now we're not going to sum anything here because we need these numbers now, and we're going to square these numbers. So we are going to x minus x bar, and we're going to square this. So taking this, we're going to put equal that, and then we're going to formula, math and trig, square root. All right, so now, like I said, it's been a while since I've done this, so I apologize. There's always a way to get around something. When in doubt, just go old school. Oops. So now it's going to square all these numbers, and now we need to add them up. So we will auto sum. So now we have 494.95. Looking back at our program, our thing that we need, now we need the square root to get the standard deviation. So now we need the square root of this number divided by n. Okay? So equals formulas. There we go. Square root divided by n. F22 divided by 20. And so there we go. Standard deviation is 4.974686. And that is how we did it just by inputting it. Now, we should be able to actually do all of these without having to do all of that. I just showed you the long way to do these. We should be able to go to statistical and look at standard deviation. It's been a while since I've done this though. All right, so that didn't work out that way. I got to figure out how to do it again. I'll figure it out. I guess just got to do some research. Like I said, it's been a while since I've done Excel, but that's the old way, the old school way of doing it was what we just did. And I'll send you all this, or I'll make this available so that you don't have to recreate it. Now, you will have to adjust things. Obviously, you have 30 numbers. You got to make more room and make changes to it, right? So use it, but make sure you use it and correctly. So a lot of data just from that one little table, right? Is it, everybody leave me? Okay. Now, we can also do quite a bit of other things too. With this, we can make graphs. Let's see. So we can do scatter plots. And this is just quick analysis here. Go to charts. You can make line charts. And all kinds of stuff. So I just found this out. You can actually just do the sum, you can do the average, you can do the count. So pretty cool. But these are be helpful. Should be able to actually turn these into frequencies too. If you wanted to do that, you could do it manually and have a frequency column set up. So that is that. All right. So that pretty much covers most of that chapter. We've got some z-scores to calculate. That is how we do standard deviation and all that. You want to do some z-scores? What do we got as far as here? Okay, so page 9, we've got to fill in the missing information in the following table, representing, page 138, number 9. This is going to be how we fill in for the z-score, okay? We find that it's normally distributed with an x bar of 72 and an s of 9. So with that information, we should be able to figure it all out, okay? So z-score. And really quick on our table, we've got Ken, Drew, and Cecil. So let's put that up there. What's that? What letter? Oh, no. So we're given 73. We're given 1.55. And we are given the 82nd percentile. Other information that we're given, right, is that X bar is 72. X bar is the same as mu. And S equals 9. Okay. So let's go back to our z-scores. So we're going to want to go back to page 127. Now, our z-score is equal to the individual score minus the X bar, all of it. So I guess I should put parentheses here. All of it divided by S. So that's all we got to do. Now, we know that for Ken, so if we're going Z score for Ken is going to be equal to, we have X, right? 73 minus, we don't know what, actually we do 73 minus X bar is 70, the X bar is what, 72? Yep. And that's going to be divided by S. So S is 9. So 73 minus 72 divided by 9. is going to be our formula. So now we just make that formula happen. So 73 minus 72. With word problems, it's always easier just to write everything out first and then actually create the formula. So there we go. Ken's z-score, we can now fill in with 0.111111 and on infinitum. So we just figured that out. Now to look at his percentile rank, we didn't really go over that. So let's do that now. So if his z-score, and you got to turn to the two charts that we talked about earlier. If his z-score is 0.111, we got to find 0.111. Now, his z-score, the area in between that is 0.0438. So his percentile rank is just above average, right? So if it's on the other side, if it's a positive, which it is, 0.111 is positive, then we have to add 0.5 to it. So his percentile rank becomes 0.5438, or it's a percentile rank, right? So 0.54 is actually 54%. So he's in the 0.5438 percentile. All right. Do you see how I got that? Are you sure? Okay. So you got to refer to the chart for this one. Page 130, 130, and 131. So if it's a positive number, you are going to add 0.5 to it. If it's a negative number, you're going to subtract 0.5 from it and make it absolute value. Does that make sense? For the percentile rank, just right. So if you go to the left, if it's a negative, you're going to subtract 0.5 from it and then make it absolute value. And then if it's to the right, you always add 0.5 to it. Okay? So now let's look at Drew. I want you all to walk me through this one. So we've got Z Drew, and we know that we want to get, now we're looking for his score, his actual score, right? So what information do we have given to us for this? We don't have his score, right? So that's still an X. So what else do we have? The next thing, do we have X bar? What's that? We have his Z score. So you're right. I should put it in here. We know that Drew's Z score is 1.55. So that we do have. You're correct. I should have put it in there. What we don't have is his actual score, his raw score. So that stays in X. So what value goes in the next thing? The X. Yep, there we go, because we have our formula right there. Z equals X minus X bar over S. So we got to put X bar in there. What's X bar? It's all given to you right there on the screen. Is it big enough for you guys to read? No. Is the screen big enough for y'all to read? There you go. Yep, 72, because we have our data right here, right? So that's the stuff that was given to us. So, and then divided by what? Divided by 9. And why is it divided by 9? 9 is equal as DS, is the standard, right? So the sample deviation for this case. So now all we have to do is solve for X. Okay, so again, this just goes back to simple mathematics. If we're going to solve for X, it takes a little bit of magic here. I'll show you the actual formula here in a second after we solve for X. Okay, so after doing a little bit of algebra, we get actually X equals, and I'll put it in the Z formula experience, right? So X equals X bar plus S times the Z score. So when I solve for X, this is the new formula I get. So when I plug it into that, so X equals 72 plus 9 times 1.55. So that's our new formula, and the answer is 85.95. So now we can plug that into the table, and that was his score, right? It makes sense that his score is bigger than Ken's score because his Z score is bigger than Ken's score. So he did a lot better than Ken did, as this is evidenced, as well as now to find the percentile rank, we have to look at our chart, go back to page 130 and 131. I want somebody to tell me what they think the number is that we're starting with. So we've got 1.55. We need bigger charts, actually. So that wasn't a very good question. Well, now we're looking at where he falls on the percentage scale, right? We need to finish Drew's out, so we're looking at where's he fall in the percentile rank. Well, I'm looking. Yeah. I wonder if there's tables in the back. There might be tables in the back that we could use. Yep, there we go. Okay, so if you go to your appendix, we actually have the rest of the tables. So go to page 431. So now somebody can give me the answer I'm looking for when you use the table. So 429 to 432. So now somebody tell me what his percentile score will be at 1.55. So that's the area that's left behind. So we want the middle column actually. Okay, and what else do we need to do to it before we give our answer? Which side of the mean is it on? Right? So what do we have to add to it? Nope, I'm sure you didn't. If it's on the right side, we have to add something to it. If it's on the left side, we have to subtract something from it. And if it's halfway point is 0.5, there we go. So we add 0.5 to it, and it makes it to the 93rd 0.944. So because you're adding on to it, the area beyond Z will be the part that we use next in chapter 8. The area beyond Z is the critical value. So that's what we'll use that part for. Right now, we want to add on to where we're at, right? So that's why we're adding the 0.5 because it's an extenuation. So it's the area in between the mean and the Z that we want. Does that make sense? Because we're looking at percentile rank, so how far from 0 is his score? And 0 being all the way on the left-hand side of the curve. So mean being in the middle of the normal distribution, everything that we add on to is that side. Does that make sense? Okay. So we don't want to, I mean, you could also, if you wanted to do it that way, you could subtract the area beyond from 100 and you get the same score. So you could use both or either one, but whichever one works for you. I think it's easier for me to add 0.5 than it is subtract those little numbers from 100. Or actually it'd be 1, but all right. Now we've got some really interesting stuff. Now all we've got is the percentile rank. So now, given that we have the percentile rank, what have we got to figure out? Well, we will, but before we can solve for x, we also need to solve for z. Yeah, because we don't even know what a z-score is. We do. We have an inclination because Cecil's got in the 82nd percentile. So what do you think we need to do working from the percentile score backwards? Well, I'm willing to bet you're going to have page 430, 430, 429. You're probably going to have to use this chart to figure it out. Nope. Nope, we don't have to worry about the formula yet. We got to figure out what his z-score is, but all we are given is the percentile score. There you go. That's a good start. Yep. I would still use the little middle one. Yeah. So remember, it's 0.82 minus 0.5. So now you go back to your charts, and you're not going to find one exactly. Right, so you can either go with the one that's above it or the one that's below it, and they're pretty close, I think, either way. So we can go with the 0.92. I think that's sufficient. So now we have a z-score, right? So we know that it's 0.92, and that it's going to equal, we don't know what his x-score is, right? We do know what x bar is, though, right? Yep. And then we're going to divide by s, which is 9. Now we can see that this formula is the same that we used for Drew earlier, so we can change it into this formula because we're solving for x again. So now we're going to do that. We're going to put it in, and we're going to know that x is going to equal x bar, which is 72. We are going to add 72 to 9 times the 0.32, right? Or sorry, yeah, 0.32, right? Because that's our x, or that's our z score, right? Was 0.32. Uh, no, I didn't for it. I didn't do it. Oh, sorry, I was looking at the wrong number. Oh, yes, figure that out. But see, there we go. See, garbage in, garbage out. But now we got it right. So 0.32, that means it's still positive, right? So we should expect it to be bigger than the mean. 74.88 is bigger than the mean. And so it's probably pretty close, right? That good enough? The mean is X bar is 72. That's the mean. So the mean can be called mu, or it can be called X bar, or the average. I mean, there's lots of different words for the mean. But there we go. That, that's actually pretty. Y'all did pretty good. You understand how to do those things? Okay, and that's okay. I've got it all recording. So it's capturing our communication and all that, but it's not capturing what I'm actually doing on the screen. But you're going to have this. I'm going to send you the Excel file. So you'll have all this, and you can work it through as you go through. Or I guess I could actually. Let me see. 1 second here. I'm going to do a new share. If I can. How's that? Can you see the screen again? Okay. Yeah, but now it's actually going to be recorded. So anything that we do from this point forward will be recorded on here too. All right. So that's chapter 5. Any other questions on chapter 5? We did mean, median, mode, average deviation, standard deviation, and z-scores, how to figure out all the other things from z-scores, including percentile rank. We filled in our little chart. Oh, no, we didn't, did we? Okay. 74.88. And then 0.32. So now if everybody had solid scores, I'm willing to bet that this is actually 86 and this is probably actually 75, which would still give us the same numbers. So I would be okay if y'all hand me in 85.95, especially if I could see what y'all did. So should be good. Any other questions on chapter 5? I don't think we're going to have to spend so much time on chapter 6. I'm going to put this up here. I'm going to knock everything down a little bit so that I can separate chapters as we go through the process of. Yeah, I can do that too. Just remember to actually look for it though. Oh, yeah, I've got other little buttons everywhere from the other stuff that I'm using to actually show you all this. So I'm trying not to hit those buttons and stop things from happening. All right, so chapter 6. And if you look at the end, or so like chapter 6 has all kinds of really cool on page like 171 through 176. There's pointers on how to use like Excel and things like that. But it's kind of cool. So there's some there are some step-by-step instructions on how to use Excel to do different things too. And we'll probably use those as we go along and go through this. So this actually is a pretty short chapter. It talks a little bit about probability and how to figure out probability. We're not too concerned with dice and with flipping coins. There are some rules of probability, though, that matter to us. So the probability of a series of independent outcomes occurring on successive trials, I'm on page 184. This is also known as the AND rule because we want to know the probability of one event and another event. So basically the multiplication rule applies in like cards. So there's 52 cards in a deck, right? And so how they figure out the probability of receiving the card that you want determines the cards that you already have, and by the other things, right? So if you're looking for a flush, that means 1 out of 4 cards is available, unless of course you take them out because you have one in your hand. So now the next probability is not 1 out of 52, it is, or not 1 out of 4. It changes because you have one in your hand, so that means there's only 52 cards left, or 51 cards left. So now you only have a certain percentage out of 51 cards, and then 50, but you multiply each one of those every time. Here with the coins, it's easy because it's 50 times 50. It's a 25% chance of flipping. The second coin is flipping to be a head or a tail overall. And then if you did it a third time, you just keep going on success. The addition rule, the probability of one outcome or another outcome occurring on a particular trial is the sum of the individual probabilities when the two outcomes are mutually exclusive. This is known as the OR rule, and we want to know the probability of one event or another event. And so the probability of tossing a head or a tail on a single coin toss, we sum the probability of each individual event. So with only 2 events, 2 possible outcomes, the chances of you tossing a coin and getting a head or a tail on the second event is 100% because you're going to get either a head or a tail. So when we add them, that's why you get 100% there. It's kind of funny. Anyways, moving on. 185, page 185. We are now looking at that same chart that we looked at before, only now we're looking at the whatever is beyond that point. So we can see that each little section accounts for, in the middle, 34%. So just the 2 middle sections account for 64%, or sorry, 74%, or 7. Let me get it right, 78%, right? No, 68%. Man, I need to get something to drink. I'll be right back. All right, I'm back. Okay, so the percentage of it happening between -1 and 1, there's a 68% chance that it's going to happen between those 2 spots. If I want to know between -1 and 2, I just keep adding all these different percentages. So 68 plus another 13.5, you can do the math. It goes up to 81%. That there's an 81% chance that what I'm looking for is going to fall on those. Now, if I'm looking at from all the way to the left, all the way to the right, I can just keep adding all those up, and those are the chances that's going to happen. So it really depends on what you're looking for to fall in certain ranges. So and this is important because we're going to start testing hypotheses later on, and this is what we're going to do it by looking at what is the likelihood of something falling within that range. Does that make sense? Okay. So when we look at the probabilities here, because that's what we're talking about, on the curve. So on page, well, any of the pages after page 185, I'm looking at this chart right there. Each one of those deviations, standard deviations, has a certain percentage with it. So given just normalcy, most people are going to fall just in the normal range, -1 to 1, right? Because there's a 68% chance, actually 68.26% chance that people are going to fall in that range, because that's where majority of people are. If we go to 2 standard deviations, so -2 to 2, we're going to add another 27 some percent. So we go from 68 to 95% of the people are going to fall in that range, right? So now we're dealing with just the outliers. When we go out to the 3 standard deviations, we're talking 98% of the people are going to fall in that range. And then it goes out, or actually 99% of the people are going to fall in that range. Anything beyond the 3rd deviations, we've got less than 0.26 people going to fall in that range. So as we go through and we're looking at the probability of something happening, we're looking at, as you flip the pages to the book, the shaded part are the proportions or the probabilities of something happening, whatever they're talking about. I'm not too concerned about that right now. What I want to get to is the null and the alternative hypothesis testings, okay? Because that's how we're going to apply this. And rather than talking about it and then adding this on, I think we might be just better off talking about it all as a whole, okay? All right. So remember from class last 2 weeks ago, we can't prove anything. So science is actually geared towards disproving things. If I can disprove it, then that's okay. So we've come up with a system where we have a null hypothesis, which is H0, and then we have an alternative hypothesis, which is HA. Do you see that on page 191 or 190, either way? So when we're trying to write our hypotheses, we want to do it in a way that the norm is the null hypothesis. So what we're saying is that there's no difference between the population we're studying and the population that exists in the world. The alternative hypothesis is the one that we want, but we only get it if we can reject the null hypothesis, okay? It's kind of confusing, but we'll get it as we go along here. Now, there's one-tailed and then there's two-tailed. So one-tailed hypothesis gives us a direction. So in other words, my null hypothesis says that the population is less than or equal to the regular population. Or it could be the other way, but usually it's that way because we're trying to show that there's an increase in something often. And then the directional hypothesis is saying that the alternative hypothesis is saying that this population we're looking at is greater than, because if the other one was less than or equal to, it can only be greater than the population. So when we're doing our data research and data collection, we're trying to show that what we've done, maybe it's a reading program or whatever, has increased the reading capability of 3rd graders. That's a one-way direction. It has increased. So these students are actually better at doing what they're doing because of our program. Does that make sense? So that's the null hypothesis. So let me write one out for you. So we have H0. This is our null hypothesis. And what we're saying is that the sample is equal to or less than the general population. Now our alternative, our HA, HA is, now I really should be using underscores and things like that, but I don't have the time to do it. So that our sample is greater than the general population. And so when I collect my data and we look at it as in that graph, so if we go back to, so for instance, say we're looking at figure 5.7, or sorry, 7.5. Did I jump a whole chapter? I did, didn't I? Why didn't y'all say something? We can go back. Okay. It's not a big deal. We can still go back and go, but remind me to do chapter. So this is chapter 7 now. It's okay if we did these out of order. They don't necessarily have to build on. I'll at least cover this part. I don't know how I did it. I think it's because chapter 6 is such a small chapter. Sorry about that. So when we go back to our charts, well, I threw myself off because now that I went to chapter 6. Okay. So back on page 187, we're actually probably better on 186. When we look at our hypothesis, the dark blue part is where we want to be so that we can reject our null hypothesis, which is saying that they're the same. Our alternative hypothesis, we want it to be in the blue part there. And this is just very generic. So that's what we're trying to do. And the one that I've given you is the directional one. So this is a one-tailed Z, one-tailed Z. We'll just say it's a one-tailed Z test hypothesis. Okay, now this one is going to be a two-tailed. So we're looking for HO to be the sample is equal to the general population. And our HA so we've got the ho and the ha. Our sample is not equal to the general population. And now this one is a two-tailed test. And it could be a Z test, it could be a T test. And the reason why it's a two-tailed test is because it will look like On page 189, we're looking at testing the proportions both ways. So the general population would be the not shaded in part of that figure on 7.7. Does that make sense? We want our people to be in the blue part, the dark shaded part of that test. That's where we want our results to be, yes. Because it's outside of the general population. We want to show that there is a difference, but the way that we do it is to say that there's not going to be a difference. It's kind of weird. So do you see the difference between the one-tailed and the two-tailed? Yeah. So now we've got error that we have to be concerned about. So no matter what research you do, there's going to be error. You can't escape error. So when you look at table 7.1, it's on page 192. Now, the assumption of this table is that the truth is actually known, okay? But there's actually a truth out there. We don't know it because we're experimenters and we're trying to find that truth. So when we look at the researcher's decision, if we reject the HO, reject the null hypothesis, but it is true, that is a type 1 error. Okay. So this is a really hard, I mean, sometimes I even get lost in it even still. So it's a pretty difficult concept. Okay, so when the HO is true, but we reject the HO. So what it's saying is that the sample population that I've got is different from the general population. So I'm rejecting that, but it turns out that the sample population was not different than the general population. So this is a false positive test. I think on the video that I shared, I talked about it as I went in for a drug screen, I took the test, and they told me that I failed it. I tested positive, even though I know that my sample was clean. I still popped for the bad test. That's a bad thing, right? You're like, oh no, I know that I know that I haven't done anything. So then they retest it and hopefully they verify that no, yeah, you're right. They made a mistake. It made a type 1 error. Okay. So it rejected that, hey, Dave's urine is clean, just like everybody else's urine is clean. That was the test of that. Well, it said that nope, Dave's urine is rejected. It's not clean, even though it was clean. So that is a type 1 error. That's OMG, right? For women, it's when you get a false positive on a baby test, right? That can be good or bad, depending on what you're trying to do. So it might be a false positive, depends on your perspective. But if it says that you're pregnant and you're not pregnant, that's a false positive, right? I have right. So now you really see, and now you can understand how important like things like testing are. and how important it is that it be accurate, so that we don't get those false negatives or the false positives. The false positives are worse than the false negatives, though. So when there is no difference in the population and the sample, and it's not rejected, then that's the correct decision. Okay? Does that make so when there is no difference and we don't reject it, that is the correct decision. That's when the HO is true, there's no difference. We don't reject the HO, we keep it. That is the correct decision. So that's the first column there. Type 1 error and the correct decision when the HO is true. The type 2 error goes in the next column, which is, so the HO is false. We need to reject it. So if the HO is false and we reject it and say that it is false, that is the correct decision. Does that make sense, right? When we fail to reject it, even though the HO is false, then that's a type 2 error. That sucks too, because you just got a really poor sample and it told you that, nope, there's no difference here, even though there was. That's not as bad as false positives, though, right? So false negatives aren't as bad as false positives. It still sucks, though, because then you wasted all your time, or you feel like you wasted all your time. And you're like, man, I know there should be a difference here, but there wasn't. So I can pretty much guarantee you that there's going to be some kind of questions regarding type 1 and type 2 errors. So do your best to try to, if you have to, watch this portion of the video and try to think, how did Dave explain it? It's kind of hard to grasp sometimes because we're trying to disprove something, and when it's not disproven, that's a good thing, which is hard to kind of understand. All right. Then the other thing is statistical significance. Just because something is statistically significant, it depends on like power, it depends on a lot of other things as to what it says. Just like I told you that first day of our second day of class, first day, when we went over that article with the military, right? Yeah, they showed that there was a difference, but the information was skewed because of the population that they chose it from. That population already is known to have a higher ACE score. So therefore, they got significant results, but also in some ways, it was already geared towards significant results. So it's kind of like a form of confirmation bias. Does that make sense? Because you're picking not from a random sample, you're picking from a sample and you're using a random sample test, like what we're going to talk about after we go back to chapter 6 and talk about chapter 6. So, well, that's, pretty quick, down and dirty. That's chapter 7. Not a whole lot to it. There's a lot in there, but not a whole lot to it itself. The biggest thing to know is that the null hypothesis is what you want to reject. The alternative hypothesis is the one that you want to take. By rejecting the first one, you take the second one. And so you're almost always comparing the sample to the regular population, and they're the same in the null hypothesis. In the second one, you're showing that there's a difference. If there's a one-way difference, so if it's a directional one, then it's going to be a one-tail test, whether it's a one-tail t-test or one-tail z-test. If you're taking it and you're trying to prove, or not prove, but show that you don't care which direction it is, you just know that there's a difference, then that's a two-tail test. The one-tail test is more powerful than the two-tail test. And we'll talk more about that when we get to chapter 8. That's fine. I'm recording this, so I'll post this up later. Anybody have any questions on chapter 7? Okay, then let's jump to chapter 6. Maybe. So now we are going to use um, data and compare it to other data. So we're going to start using correlational values. As we can see, looking at the scatter plots, I'm now on page 150. On page 151, actually, we can see that there are scatter plots. There's scatter plots that are positive on, like as an A, negative. C, there's no relationship. In D, it's a curvilinear, so it goes up and it goes back down. The only ones that we can use for correlational data are A and B. Okay, you cannot use C or D when it comes to correlational data because there's nothing to correlate. If it's that curvilinear, there's different tests for that. So we wouldn't use correlational, we would use a different test for curvilinear. A negative relationship, well, as one goes up, as one variable goes up, the other one goes down. And the positive one, they both go up in the same direction. Kind of like weight and height. Tends to be the taller a person is, the more they weigh. The biggest thing to get out of this is to understand that A, we can never take correlational data and make causal relationships out of it. So we cannot do that. There's no directionality often with that. The third variable problem, sometimes neither variable may actually be interacting with the other. They may be interacting with a third variable that you don't know about. So a lot of times people collect a lot of data and try to take out other variables to see if there's an actual relationship between the two variables they're interested in. It's easy to take data and just take one little section. So on page like 156, you've got the whole range of the SAT scores from 400 to 1600, but somebody might take that data, truncate it to where you're only looking at 1000 to 1150. So out of that whole range, you're just looking at very little data. And you can still see that there would still be a relationship there, but not as strong as the other relationships that you can see when you look at the whole range of data. So when we do statistical analysis, some analysis allow us to predict, others we're just basically talking about the general relationship. So we can't always predict because without doing a regression analysis, just using the Pearsons or the other components, we are just using it to say that, yeah, there is a relationship. As one goes up, the other one goes up in general. Doesn't necessarily mean that there's a whole lot of people. So when we look at the height and the weight, it's easy to see. We could actually set this up ourselves so you can see how to do it. So we've got the X for weight, and then we've got the Y for height. And when I put data in here, is 105. And looking at the adding the height. All right, hopefully I got them all in there correctly. So once we have that data in there, we can start looking at the different things. So looking at the Z score for X, again, we're using standardized scores, right? And the Z score for Y, we just have to calculate each of those. So when we look at it, X minus X bar, or mu, so we just need to figure out really quick what the means are. Again, going to our formulas, we just get the sum of that and the sum of that. And then we get how many is that? 22 minus 3, 19. So now looking at the average for this, I think we can actually just average. It's 149.25. And then here, formula average 67.4. Looking at our Z scores here for X, the weight. We get to the Z score. Put those over there. First thing we have to do is get our Distance from the mean, correct? Rules. Minus so that is all of our distances from the mean, and then we just need to do the absolute value. All right, we're getting there. Sorry for I'm sure this is not so exciting for the two of you who are left. All right. So now we are looking at the sum of zx and zy. Or I should say the multiplication of zx and zy. So, I didn't do the z yet, so sorry. We're getting there. Divided by the standard deviation. And that's also in the book too, so I'm just going to use the books. So later on, I'll add another column that actually does the calculations for us. So for the z and the y here. Great. I actually had it right the first time. I didn't want to make it negative or positive. Okay, so the z of x is then x minus x bar divided by standard deviation. So now we've got equals x minus x bar, oops, divided by the standard deviation, which is 30.42. It's not x. And so 1.6. Yep. Divided by 4.57. And then we have zx times zy. And so there you go. That is the Pearson's coefficient, which means that to interpret this, it's positive, so they are related positively and very strongly. Looking at page 163, you're going to use different coefficients for different variables according to what type of variables they are. For Pearson, you can use it for Pearson's for interval or ratio. Spearman is for both variables as ordinal or ranked. Point by serial. One variable is interval or ratio, and one variable is nominal and dichotomous. It has to be nominal and dichotomous. And then phi or phi, both variables are nominal and dichotomous. So those are the different formulas to do for this data. Let's get it set up. So here is our data, with this being our height, this being our weight, and this is just the first series. So we want a linear line here. And that will give you everything that you need to know. So that is how you get the r squared and the intercept from this line. This line right here is the regression line. And so each one of these dots is equidistant from this line. And so the data that we need for understanding it is in this line, y equals mx plus b. So if we were going to use this to predict somebody's height or weight from any of the data given, then that's what we would use. So that is regression analysis used as predicting. And everybody is gone, so I guess we will not go on to look at the chapter 8.